Hello everyone, welcome back again. This is a video tutorial for chapter 3, which is dam outlet works or spillway design. So then we will go to energy dissipation. This is just you can take from table. This is values of constants K and R1, R2, A and B. So you can take for vertical phase K2 and this one, and the rest we will see later on. Then you can calculate. So just substitute 16.33 in instead of HD. So you get this is the general equation for the crest profile. The crest profile. So the crest profile is this one. This is the crest profile. Downstream. X to this direction, Y to this direction. So the crest profile will be designed using this equation. So now, before we determine the various coordinates of the downstream profile, we shall first find the tangent point at which the curve ends. So I think from mathematics, from calculus, we know just point of tangency. Point of tangency is nothing, just tan theta, or the inclination of the line which passes through the point of tangency, which is the slope. So dy by dx equal to, you have slope, downstream slope already given. Downstream slope is this one below this point. So you have 1 to 0.7. So derivative of this function, derivative 1.85, you bring to the coefficient, then minus 1. So you get 0.85. So this is the general equation for the curve. This is for the curve. Then determine x 1 over 0.757. You get 27. This is the result. Then substitute back to the equation, to the general equation of the crest profile. Then you can get again 21.027. So plot the coordinates of the downstream profile of ogee crest. Now you start from 0, from origin. Then offset you can make 2 or 1 meter. Then up to 27.23. So you get, according to the equation, up to this value, 21.027. So you plot. This is just plotting like this. You can just plot the curve. You can plot up to point of tangency. So this is the downstream profile of the ogee crest. The next step is upstream profile of ogee crest. Upstream profile. So to get upstream profile according to USACE standard profile, you using constants A, B, R1, R2 as a function of HD, just from the table. From this table, for vertical upstream phase, you have R1 over HD 0.5, R2 over HD 0.2, A over HD 0.175, B over HD 0.282. So you simply just crisscross, then you get the value of A, this value, the value of B. You simply multiply by this from table, so you get these values. So these are values of A, B, R1 and R2 for upstream. So you go for upstream, A distance, you have A distance, this one, up to R1 distance. So R1 distance you get, once you plot this point, then R1 you go to this direction. Clear? So similarly for R2, similarly you go to B distance, 4.6 you go, then just you plot this point. So this is the total profile, upstream, then downstream. So once you complete this profile, then you can start construction. You simply fix formwork, curved formwork, and other components. Then you can fill concrete. So this is just a procedure. So how do you design just the curve? So I think second method is using compound circular curve again. You can use compound circular curve. Using compound circular curve, you have this equation. This is a general equation for upstream profile. So you substitute HD 16.33, then you may further derivate this equation. Then finally you can find, but no, you don't have slope on this one. Then just you can get the general equation. This is the general equation. So you may provide offsets, then finally you can calculate. But this curve should go up to b is equal to 0.282 HD, which means to this direction. X to this direction, then Y to this direction. So you can just substitute in the equation, then finally you get the value. So you plot similarly. So I think next step 8 is just step 8 is a reverse curve. A reverse curve at the end of the spillway or at the top of the spillway can be designed using this formula. Just R reverse R curve you provide, then this is radius. So 1/4 of the spillway height get 26. So 26-meter radius with 60-degree central angle, you can provide this curve just to guide the flow to the air in order that the downstream river region will not be damaged. So to protect the damage from scouring and erosion, you just flip to the air, just you distribute to the air, then energy will be dissipated. Then velocity of flow may be approximated. You can just use this equation, neglecting friction loss on the spillway surface. Then you can use this equation. Just you can derive from Bernoulli's equation 2g, just the square root of 2g, z plus ha minus y. So p plus hd, which is total fall from upstream water level to the floor of the downstream top, total fall. P plus hd. And ha is just head due to velocity of approach, and y is tail water depth, and v is velocity of flow at the top of the spillway in meter per second. So once you get this velocity, then R can be calculated, which is the reverse R radius. So just you have to make this one bucket type or curved reverse curve. Then this flow will just dissipate the energy in the downstream part. So I think this is important. Then as exercise, please do this. This is just in tutorial problem worksheet. You have design an overflow section of gravity dam with upstream slope of 1 horizontal to 3 vertical. You see, upstream slope you have, and downstream slope this one. Then the rest as usual you have. Then try this problem. Okay. So I think with this, if you have any question. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it.